Assalamu alaikum dear students, we're back with another video lesson. In today's video lesson, we're going to begin with chapter 6, and I can tell you that chapter 6, it is one of the most important chapters that we have in grade 12's physics. It talks about, or it is about electromagnetic induction. What are we going to learn in chapter 6, Baba? Here, the first thing that we have, we'll learn about electricity from magnetism, inducing, generating electricity using magnetism, Basha, and then also we'll talk about generators, motors, and mutual inductance. And then the third thing that we have it is AC circuits and transformers. So these are these are the things we will be talking about, Basha. The first thing that we have it is electricity from magnetism. What is electricity from magnetism, Baba? That is the first section we're going to begin with. Or you can say electromagnetic induction. What exactly electromagnetic induction is? Before we dive into that, I would like to give you a little information or perhaps maybe remind you what we've studied in chapter 5. In chapter 5, Basha, we've studied that in chapter 5. We said that if a current passes through a conductor, Basha, or a wire, that of course induces a magnetic field around that conductor. Wire be, coil be, solenoid be, hashtag be, Basha. And of course, let's say this is the coil that we have, for example, Basha. And then there is a battery here, for example, an AC source, with DC source, positive, negative here. Once the current passes through this, let's say, then of course, it doesn't matter which side, positive or negative, there is a magnetic field around, or a magnetic field was inducing or created around this, let's say, solenoid. Now, this magnetic field, it is, or the field of this magnetic field, it is almost like the same or similar to that of a bar magnet. And of course, you can say one side is north, the other side is south. Doesn't matter which side is which at this point here. Our chair was we can say Christian Hans Ørsted said this, Basha. Ørsted, you can say, discovered this relation between the two. In chapter 6, we're going to do the reverse of this. What does exactly the reverse of this would be, Kaka? Chapter 6, Basha. Kaka. The reverse of this, we're going to use a magnetic field or a bar magnet, just a magnetic field, to induce a current in a, let's say, in a circuit. Basha, what exactly this means here? In a circuit, imagine if you have a coil. Basha, this coil is connected to a galvanometer. Basha, this is just an indicator. Again, magnetity. For example, if you have a magnet, if you bring this magnet close or away from this coil, you would notice that, or you will see that there will be a current flowing through this circuit, Basha. So of course, you could say this galvanometer then shifts right and left based on the direction of the magnet or the magnetic field of this magnet here. Basha, who's the, like, for example, the scientist who discovered or devised this Kaka? It was a scientist, his name was Faraday, Basha. Now, this is exactly what we're going to do. So in chapter 6, for this section here, Baba, what we're going to do is we're going to reverse what we've studied in chapter 5. Basha, Gutman Lewe, Karentak man, agar Karentak banao conductor shida tuba, yan roishtububa, magnetic field that shidrus da kalera, agar magnetic field that manabi, that one in Karentak banao circuitak dadruskan. How do we do that? All right, just stay with us, inshallah. This is what we're going to talk about for today, Basha. Yeah. So what exactly do we have? Consider we have a coil, Basha Baba. Agar coilak manabi, and bablin solenoid declare. This is what we have. Adatan, we use a galvanometer. Isha galvanometer itsi Baba to indicate to, for example, to tell us if there was any current induced and generated and produced bablin in a circuit. Basha an issue way Baba woku indicator require agar current aglina circuit ki drus bilawkati galvanometer ka it will shift right or left, Basha. Liberty galvanometer bakardinin, because we said that galvanometer measures small amount of current. So it is obviously a small amount here. So Zor Basha, what exactly happens agar magnetic man habi Baba? If, for example, this is north, Basha, and then a bar magnet. If it is going into the coil, like in short, you will see that this galvanometer needle, Basha, it's about, let's talk about this a little bit more. Basha, this galvanometer needle, it is shifting right and left. Let's say, for example, once you bring this one, it shifts to the right, Basha. So that is what happens once you move the magnet close or into the coil, Basha. So what exactly happens once you move the magnet away from the coil? باوی copy paste کەینەوە باشە ئەدەگەر ماگنێتەکەی لە کۆیلەکە دوور کەینەوە چی دێتێ then in that case you will see that بابا right you will see that right this galvanometer needle now it is shifting to the other side باشە so based on this we can see that ئەگەر directiony با بڵێن motiony galvanometerەکەی ئەگەر change بێ ئەو کاتی also the direction of what does this exactly indicate کاتە ئەگەر ماگنێتەکە بێتە پێش کۆیل currentێک دروست دەبێ it is in a direction وانە if you move the magnet away کاکە ئەو جارە دووبارە currentێک دروست دەبێ but this time the current that is induced will be in opposite direction با بڵێن to the one that was first and there is also one more thing here Baba you can notice that the كري مثلا what happens exactly if you move the magnet close to the coil and then let it rest أجر ماغنتك ننزله what exactly happens there for example this is the coil again and this is the galvanometer here if the magnet even if it is let's draw something a bit nicer here باشا this is the coil here مانوش galvanometer here if you have a magnet if this magnet is not moving even if it is inside the coil here باشا you will see that the galvanometer needle is pointing 0. What does this mean? That means there is no induced EMF. Based on this, we can see that as long as you move the magnet, Basha, then EMF will be induced. What is EMF, Baba? That would be a potential difference, Yan, which makes the current flow in a circuit. Those are the 20 lejati or galvanometer. Or galvanometer, Baba. Basha. What exactly the benefit of this? Oh, magnet bina pesha galvanometer or this lamp here, it would of course you can say it goes bright, let's say, and glopaka ish dakatan, which indicates that there is a current induced in the circuit. Basha. If you move it away, dubara the galvanometer needle, but this time it is shifting the other way. That means there is a current induced, even though it is in the opposite direction. If you have a light bulb again, the light bulb starts to work one more time, which indicates that there is a current induced in a circuit. If the magnet is not moving here, you can see that the galvanometer is not shifting, the light bulb will not work. Based on this, you can tell or see that as long as for example, the magnetic field is changing, there is always induced EMF. Basha. And magnetic field there will be a current EMF induced. Basha. We'll talk about what is EMF in a second. Basha. And then we can say there is a current in a circuit. At this point, Baba, it doesn't matter. You can hold the magnet still, you can move the coil closer or away from the magnet, but it doesn't matter. As long as there is relative motion between the two kaka, there will always be EMF induced. You might wonder, for example, what exactly happens if you reverse the direction of a magnet here? Basha Gutman, this is what we have for a coil. If we move the north or push the north into the coil, Gutman, the galvanometer shifts to the right. You might say, how do I know shifts to the right or left? Just know that galvanometer if the north is getting closer, if the galvanometer needle is shifting to the right, what happens if you, let's say, switch the poles of a magnet? If the south is moving closer into the coil, this galvanometer needle is shifting to the opposite side. It is opposite and bubbling in the opposite direction to what happens here. Alright, what if we move, let's say, the magnet away this time? You can see that if it is moving, or if the south moves away, the current that is induced here, or you can say this galvanometer needle now, it shifts to the positive side, which means that the current induced, it is obviously opposite to what is induced here. What do we learn exactly from this at this point, Baba? The blend magnetic field and the magnetic flux. Basha. If a magnetic flux on a coil change, there will always induce EMF. But بشرتك Baba, EMF is basically, you can say it is the potential difference, not the potential difference, it is the driving force that pushes the current through the circuit. Basha? Yeah, we'll talk about this one more later. But later voltage which pushes the current through the circuit. What pushes the electron or the current through the circuit, it was a battery. When you get the coil when you have one side positive, one side negative, the potential difference here would push the electron so that to move in a circuit and no potential difference with the current circuit this change in the flux which induces an EMF باشا يعني ليرة EMF درس دبيتن أو simply EMF بابا. This is what we use here. This EMF represents the potential difference and bubbling the voltage that is induced باشا. و EMF of course you can say it is the driving force أو أوشتيكا ودكا palba electronica within so that the current is flowing through the circuit. بس قال لي بابا كمان ليرة current will flow through the circuit أجر complete loop يعني circuit if the circuit is not connected and bablan أجر gap دابو. If the circuit is not connected أوكاتي one side will be positive like it negative, but if it is not connected قال لي بابا no current can flow, because for current to flow you need to have a complete circuit, which I believe these are pretty basic, basics regarding the electrical current. Or electrical circuit, we can say. Kata, this process baba of inducing current in a circuit, that is called electromagnetic induction. Induction وكوابلي production and generating electricity باش baba. Kata, electromagnetic induction is the process of creating a current in a circuit. But how do we create current in a circuit? By changing the magnetic flux on a circuit coil. The magnetic flux magnetic flux, we've learned that it is the number of magnetic field lines that crossing, you can say, through a unit area perpendicular to that area. قلت ما ليرة أو magnet بابا ليرة شو دي بارب كينو ما بس ما ليرة تيا كأو magnet ديتا بيش لسر coil كي. You can see that if this is the coil here and this is the cross section of a coil بابا هاي دابرين. Alright, bubbling osh galvanometer كيا. Magnet data picture, let's say this north and south. When you got that, there are a lot of magnetic field lines here. Magnetic field line can هم زي north and south. But if we draw, for example, some more here, like just draw more here. When this magnet is getting closer, for example, to the coil baba, جماري أو magnetic field line بناو coil كيدا دارون, which is perpendicular to the surface or the plane of the coil. زيادة كاونية. So based on that, we can say there is a change in a magnetic flux. When the magnetic flux change baba, that induces EMF. أو EMF هو ده كاتن كرنتك بناو circuit كيدا برا. So this is the current that is induced. This is how we can induce current in a circuit. أو process baba. It is called electromagnetic induction. أو basically regarding this one. With the blend, as long as there is relative motion kaka between the circuit and the magnetic field باشا. قلت مان هركة circuitك بزوليان magnetic fieldك بقورة بزولي أو كاتي there will be EMF induced and current induced أجر بوشرتي close circuitك ما نبو. But if there's no relative motion between the two kaka, no current will be induced in a circuit. So of course there are many ways you could do that, by the way. Instead of moving a magnet close to a coil, you can move a wire inside a magnetic field. Doesn't matter, huh? The clear do magnetic pole كمان ببابا يكتشان north or يديك south ليرة doesn't matter north and south here. Later, of course, there is a magnetic field. If you move a wire, all right, that is perpendicular inside, for example, the let's say perpendicular to the direction of a magnetic field inside a magnetic field, of course, the one side of the wire become positive, or you can be negative. And if you have a closed loop, you can say that current will be flowing through the wire. Yani, shartniya how you do this, Baba. There are many methods. There are many methods to induce EMF, Basha. This is what is called the electromagnetic induction. Kata, what is electromagnetic induction, Baba? It is the process of creating current, Basha. Creating current in a circuit loop, Basha, by changing what? By changing the magnetic flux, Bablin, in the loop here. Basha, قلت ما magnetic flux هكا كده قرأ جماري أولاين أنا magnetic field داني بابا كده تسر كويلكي. When these number of magnetic field lines are changing, then EMF what current will be induced. باشكاكا طبعا current cannot be induced without EMF. كدلين current induced بو بابا يعني EMF already induced بو باشا. كاتا تواني بلين you have learned that chapter 5 بابا قلت من current in a circuit is the source of a magnetic field. كاتا كوا current بناو كويلك ده روي magnetic field لشي بدوري أو كويلي دروس ده بوانيا. This is what we have here. It says it's possible to create a current, Basha, in a closed circuit without using battery, without using any bubbling power source, Basha. Kudetwanin, Gutman, by moving a magnet close to a coil, Basha. Gutman, this is a magnet. Once you move the magnet closer or away from a coil, Gutman, lira, galvanometer it is shifting, which means indicates that or sign current اقلنا كولك يدرس بها. باشا, what about here بابا؟ قلت ما ليرة ذكر الجاتي وي wire بكاربيني that is moving inside a magnetic field, it gives you the same effect. But of course, أجر كويل بيوكاتي أو EMF يعني current يدرس دبي will be stronger than if it is just a wire. باشا, قلت ما أنا current results كاتا current تقدرس دي بابا أجر circuitك close بو باشا when it is moving with respect to a magnetic field. If the circuit moves towards or away from the magnet, or the magnet moves towards or away from the circuit, then a current will be induced. These two study tip as long as there is relative motion between the two, there will be EMF and current induced. Basha, if neither the magnet nor the circuit is moving with respect to one another, then no current will be induced. Basha, study beyond bablinki termak mani baba. That is what does say, it says induced current. Induced mabas malirati baba oikwa durisbu generate bu basha. So basha, this induced EMF, you can say it is the or it is the electric current basha induced in a closed electrical circuit by changing what? By changing the magnetic flux that crosses the circuit. There are many ways to induce EMF. Another method is by having or rotating a coil inside a magnetic field. Inshallah, that is obviously a generator, you can say, or this is how electricity generated and induced by using a generator. Like how does it exactly happen? What exactly do we have? But if there's no motion kaka, you can see that the indicator and the galvanometer needle, it is not shifting. That means there is no induced EMF, there is no current. Bash kaka. What if you, for example, move this towards the left? North is first. Then you can see that the galvanometer needle, it is shifting to the right side. Once again, Baba, kubzan right and left. At this point, you don't need to. Basha dua inshallah, but detail basi ushtaydakan. Zara tanhab zana. Once you move one of the poles closer, for example, north, it goes to the right. Basha. Now, what happens if you keep that stationary, or if you don't move the magnet, it doesn't move, which means that there is no EMF induced. You must keep one of the two moving always. You can compare this to, by the way. Compare if it is moving to the left, the galvanometer is shifting to the right. What if it is moving away from the coil or to the right here? If it is moving to the left and north, shifts to the right. If the north is moving away, it is shifting to the left. You can see that, which means that direction motion reverse bubito baba direction current reverse bubito chapter 5 damango حركاتك direction current reverse bubito direction magnetic field reverse dabo ليرة عكسه كدايركشني magnetic field يعني motion reverse دبي direction current reverse دبي توقعت تواني بلان عينا نشتليرة ليرة شتشدي كمان يا بابا. What happens if you move, for example, the magnet at a higher speed? ليرة كمان speedك you just move that at a regular speed here. باشا, what happens if you push the magnet at a faster speed into the coil? You can see that the galvanometer needle is shifting more. That means the amount of current that is induced here, it is greater at this point compared to the above one. سيدي كشمانة قد ما نقرها أدو reverse كي بابا يكم ذا north بو it is shifting to the right أدي أقر north يبيني بيشة it shifts to the other side, which indicates that the direction of the current induced will be reversed. سيدي كشمانة, what is the condition for an induced current in a closed circuit due to the you can say electromagnetic induction? Condition. What is the condition for EMF to be induced? The condition for EMF and for current to be induced, there must be a relative motion. If there's no motion, all right, or no relative motion, let's say, then no EMF is induced. No relative motion, baba, both in the same direction and the same speed. If, for example, if the distance between the two doesn't change, baba, that means there's no relative motion, even if they're moving. If there's no relative motion between the two, no EMF will be induced باشا كاتا or the magnet or the circuit or both should be moving. There are different ways baba that EMF can be induced باشا. For example, we're going to learn about 5 ways 5 methods to induce EMF باشا. بس استا ضروري سرتبشن بابا تنها بزانا. Alright, this would be best for summary, for example. We're going to induce EMF in a wire, voltage and potential difference. Just called EMF basha baba. We'll use a coil, for example, to induce EMF and current basha. We'll use this coil basha by changing, let's say, the magnetic field or the area or the angle babbling basha. And then again, there's another method which is called, you can call this one, what is it called? Self-induction basha. We'll use one coil, but if the current in that coil change, it makes EMF to be induced. That of course induces current to here, generator basha, which is a different concept, and we can also use 2 coil to induce EMF in that circuit basha. These are kind of like a what is it called, preview of what we're going to learn in this section right here. The first thing that we have baba, we'll say the induced electromotive force in a straight conductor. أو يعني كودة وانين EMFك ودوا كرنتك لناو straight conductor چی درست کن باش بابا. Consider we have a wire باشا. أو دكري conductorك بي أو هشتك بي wireك بي, like it doesn't matter باشا. So this is one of them here. Let's say this conductor is inside a magnetic field باشا. أو conductor it is, I think it's too much though. أو conductor it is inside a magnetic field باشا. Magnetic field دكري into the page B, دكري out of the page B, like doesn't matter. And these are uniform magnetic field, by the way باشا. The magnetic field correct B. So this is what happens now. We know that inside this wire there are positive and negative charges. Positive and negative charges here. This wire obviously it is neutral at this point. These are okay. Alright, so this wire you can see that it is neutral, for example. It is a conductor obviously, so it has a lot of free electrons here. What happens exactly if we move the wires into one of the sides here? Let's say we'll move the wire into this direction kaka basha. And of course now we're going to reverse the direction of the motion and then the magnetic field as well, see what will happen exactly. In chapter 5 we've learned that, alright, when a charge is moving at right angle to a magnetic field, there would be a magnetic force on a charge. That was chapter 5. Magnetic force will be QVB. QVB sine theta. But later, here's what we're going to do. We have a conductor that we're going to move this inside a magnetic field. By using the right hand rule, you can find the direction of a magnetic force on this wire here. Direction magnetic force direction magnetic field your thumb direction motion basha. And then get positive B force will be out of the palm, get negative B the force will be out of the back of the hand. As now you can see the direction of a magnetic field that is into the page. So direction motion let's just do that here. It is to the right. And then let's see what happens exactly, or what will be the direction of the force on these charges here. With my magnetic field into the page, that's what you're going to do. Direction motion there. According to the right hand rule here, so there will be a magnetic force on a proton, so positive charges that push them downward. What about the back of the hand? Because we have both protons and electrons, we have them both here. Protons will be pushed downward, protons will be pushed downward, electrons will be pushed upward. But protons will be pushed downward because they are inside the atom here, inside the nucleus bubbling. If you want to move them, you have to break the nucleus, which that is not possible at this point here. But what exactly happens? How many electrons will be pushed upward because electrons can move. Once electrons can move, there will be less electrons here, so you can say positive charges dominate Janish, it becomes positive. But electron will be pushed to this side here. This side will become negative. Because electrons have left, become what? Become positive right here. كواتا استا لنا أو wire بابا. We've induced an EMF. باشا. أو wire استا it's something like one side of the wire is negative لكن ديكا positive. What does this remind you, Kaka? Isn't this reminding you of a battery? Battery baba. This remote control, for example, battery here. One side, for example, is positive, the other side is negative. And that is exactly what it is. So that this battery has a potential difference. That means, of course, there's a potential difference. If you connect a wire with the battery or a light bulb, now current can flow through this circuit here, and now we can turn on the light bulb here. But because one side is positive, one side is negative, that positive negative, it is called EMF. Bash Baba. EMF, you can say that it is equivalent to the potential difference here, or equivalent to the voltage here. Bash Kaka. But remember this, Baba. Volt or voltage here. Basha. Agar potential difference, adatan we'll use this for battery like or DC like. Basha. When we say EMF, Baba, this is for something that is generated, or we use this for, you can say, AC circuits. Basha. This EMF, it is still measured in volt agad. Alright, so now just by moving the conductor inside a magnetic field, that should be positive, that should be negative. Basha. That's like what exactly happens, and this resembles a battery now. Basha. So what exactly happens if we connect that with a light bulb here? Light bulb right, and then now connect both sides to this. You can see that the light bulb starts to glow, even though brightness of light bulb will not be that much, because this EMF that is induced is very, very little. Negative, positive. That is what happened if we move the wire to this direction. What exactly happened again? Right, so remember this. Alright, so hopefully we could do this one real quick again. What happens exactly? Magnetic field is into the page. Now what happens this time if we move the wire into this direction? Right hand will the magnetic field into the page of the direction motion. Let's see. Magnetic field direction motion. Let's write magnetic field here as well. Basha. At this point here, Baba, you can see that this, or the upper side, will be positive, the lower side will be negative here. By reversing the direction of the motion here, the polarity will be reversed as well. That is one of the things that we have. Basha. Direction and polarity. You can call this side A and the other side B here. Polarity. Polarity baba the beta positive the beta negative. What does it depend on? Depends on the direction of the motion here. If we have inside a magnetic field, of course. Again, now you can say in general, depends on the direction of a magnetic field and the direction of the velocity as well. But later, if we have a uniform magnetic field, magnetic field direction constant, then if that is the case, it depends solely and only on the direction of the motion. Basha. Oh, I get direction of magnetic field into the page. What if the direction of the magnetic field is out of the page? Because I know you might wonder here. Direction magnetic field it is out of the page. You can see it as a point one, yeah. Alright, so let's move this one here first to this side. Oh, magnetic field direction or direction motion. We're not gonna do this because we'll have to do this time here, because it is out of the page, right? So this not the direction of the motion, is the opposite, right? If you do this, the force on a positive charge will be upward. The beta positive, the beta negative. Basha? Yeah, but if the direction of a motion to the other side the goratan. Basha? Baba, whether, watch this, there's one thing you need to know. Whether the wire is connected to a circuit whether we have a closed circuit closed baba, as long as you move a conductor, any conductor, inside a magnetic field, conductor beta positive beta negative EMF EMF is induced. But do we have any current flowing in a circuit? No, because you don't have a current in the first place. I mean, you don't have a circuit in the first place. That's got the current baba. Only when there is a closed circuit, then current, electron, can flow through the circuit. We know that electrons will be flowing from negative to positive. It is always opposite, or you can say from positive to negative باشا اگر لو دو خاله بيتي بس يكشي ديكش معناه بابا as long as there is relative motion here between the wire and the magnetic field EMF will be induced اگر relative motion نبو استا يك دو خال ديكش شي باستكن if there's no relative motion between the wire and the magnetic field اوقات no EMF is induced بس يكشي كيه بابا استا ما قلت مان EMF induced بيوني but how much EMF will be induced باشا equation معناها for the EMF induced we'll say for a wire يعني conductor doesn't matter right straight conductor though باشا وكات دكات بابا دكات B L V باشا or you can say believe in sine theta here وأجاش اللي بي بابا قلت مان this EMF that is induced will be maximum أجر قوشيان the angle between the magnetic field and the velocity if it is 90 باشا أجر the angle between will be maximum أجر theta between باشا between B magnetic field and V is 90 باشا will be maximum. When will it be zero كاكا؟ قلت مان it will be zero أجر theta بيني بيو باشا بيني بيو بيني V it is zero. When will it be half of maximum؟ كاكا it will be half أجر قوشكا it is 30 degree between B and V باشا because sine 30 دكاتا half أجر لو خالا نبي كاتا what does it exactly depends on بابا the EMF induced depends on the strength of a magnetic field you can see that is directly proportional to each one of those here باشا EMF it is directly proportional to the B magnetic field strength it is also directly proportional to the length of a wire أو ما بس تتبع بس ده magnetic field كزياتر بيتن EMF كزياتر درس دبي so you could draw more magnetic field lines here دير length كي بابا قال لي بي أو length it is only the length of the conductor that is inside a magnetic field ده ما علاقة من بويدانية conductor سندريجا كنا علاقة من بلنثي أو بالين conductor كي هي كولنا magnetic field كده هي زور باش and then this is V which is how fast the wire it is moving inside a magnetic field here and of course the direction to here زور باش got directly proportional to the length as well and also directly proportional to V and also directly proportional to the angle between B and V بابا بس كذلك directly proportional ده بي أو angle اللي بيني صفر نوتي دابي because then the bigger the angle the more the EMF قلنا لنوتو بسريع أوكاتي the bigger the angle does not necessarily means the bigger EMF in here because if you increase from 90 to 180 it starts to decrease and 180 becomes zero anyway just remember this كاكا عندك alternative شمان هي أجر قوشك الصفر يعني ستوش تابي EMF كالصفر أجر قوشك النوت يعني دو سطح تابي in that case it is maximum باش كاكا قلت مان 30 يانيش 150 أوقاتي دبيتا half بس أوي كالي رجلين قبابتنها 90 30 0 بزانا on the بس alright so you can see that if I ask you what does the induced EMF in a conductor depends on Baba it depends on four things here the strength of a magnetic field the length of a conductor the velocity of let's say the conductor the angle between B and V depends on these things باش كاكا قلت مان EMF كدرس دبي whether there is a closed circuit يعني بس current will only flow if there is a closed circuit باش كاكا سكاكر circuit closed نبي EMF cannot يعني عفوا current cannot flow through the circuit قلت مان أو خالا نبكا بس ما كنت بابا زور بس يدلا consider conducting wires pull through a magnetic field as shown here قلت مان charged particle moving with a velocity at an angle to the magnetic field will experience a magnetic force when دا قلت مان according to the right hand rule قلت مان magnetic force will be perpendicular to both the magnetic field and the direction of the motion of the electrons or the current you can say so that of course we'll say for a positive charge the force is directed downward according to this diagram Baba because you can see that here direction motion it is to the right and then the magnetic field is outward or Z positive when that if you do this قلت مان direction magnetic force it is out of the palm which يعني خواري دي بيتا positive Baba دي سرج دي بيتا negative when this is what we have For a negative charge, Gutman, the force is upward, you can see here. This effect it is equivalent of replacing a segment of wire inside Yan bubbling and a magnetic field with a battery that has a potential difference or EMF. We say that between the terminals. When you Gutman, the polarity baba. Polarity which side is positive or negative basha depends on how the wire is moved inside a magnetic field. أو لو زاريش هاتيتو باشا قلت مان polarity كي depends on the very magnetic field كيف فيكس بابلين كاتا only depends on the velocity ليرة زور باشا as long as as long as the conducting wire moves through the magnetic field, EMF will be induced. Moving a conductor inside a magnetic field produces EMF inside bubbling whether the circuit is closed or not. But scatter current be only, all right, current will be induced only if the conductor has a closed loop. قلت ما ليرة magnitude bubbling EMF كيكوا درس دبي تصنك بابا دكاتة BLV sine theta. Some people prefer to call it Believe whatever, but these are entirely up to you. Just to remember, by the way, when يكشد ما ليرة باشا باسي متكان كين بابا قلت ما دبي maximum if it is 90, minimum if it is 0, or parallel you can see half of maximum tilted or specifically at an angle 30. But later, let me talk about the unit value. EMF dakata B L V sine theta. Sine doesn't have a unit. EMF it is measured in volt. V magnetic field measured in Tesla. Measured in meter. Velocity is measured in meter per second. So meter you can say that is meter squared. You can say Tesla meter squared over second. Basha. But actually, most of the time the question is asking about Tesla. What is Tesla equal to? We know that the unit or the SI unit for magnetic field is Tesla, but subject بدكاتة EMF لسر LV EMF لسر LV EMF كبابة is measured in volt. Later length is measured in meter. V measured in meter per second. كاتا أو second ده تيتا سريع باشا ده بيتا volt second لسر meter squared باشا اگر لو خالي بزوزور جرينجا زور باشا تسيدي كش معناها what does the induced EMF depends on كاك هر كاتا قوتي what does something depends on اگر يكوشني هبولي خود بينو سبابا قلت مان BLV sine theta كاتا depends on these things here باشا لقل theta كش where's number 2 didn't write 2 1, 2, 3, and then there's this 4. Bashkaka depends on the strength of a magnetic field, depends on the length of a conductor inside a magnetic field, depends on the velocity at which the conductor is moving through the magnetic field, and also depends on the sine angle between the direction of a bubble in the motion and also the magnetic field. طبعا وكو برسالة شي حسابي ما لسرني بابا بس of course it's possible to make a question and then do some calculations about this. But so which of the following equation correctly to calculate maximum induced EMF bubbling and electromagnetic induction and electromagnetic to be electromotive force in a straight conductor. Basha? So electromagnetic induction, EMF baba stands for electromotive force, by the way, and a straight conducting wire. Basha, in a straight conducting wire, BLV, and because it says maximum, kata angle and bubbling sine 90, which is equal to 1, Alright, what else do we have now? So we're almost like done with wires, kaka, or with conductors inside a magnetic field. The next thing that we have is, we'll talk about the angle between a magnetic field and a circuit affects the induction. What exactly this means, kaka? And you know what is a coil, So for example, this is a coil here. And so let's just draw something here. You might say this is a solenoid, kaka. Of course, you could draw a coil too if you want to. Solenoid is also a coil, by the way, but it's a different one here. So this is a coil of a single loop, you can say, or a circular loop, and that is just one here. Magnetic flux just in case. If the magnetic flux will be maximum if the magnetic field lines are crossing or let's say passing through the unit bubbling through a unit area perpendicular to the surface and to the plane of the loop. Magnetic field if it is perpendicular to the plane of the loop and to the cross-sectional area magnetic field so for example, this is the coil here. Okay, in this case, of course, we get maximum flux. Chapter 5 bas What if, for example, if it is at some angle here? What if it is parallel? let's just say some angle here. That's the coil here. Y could scalar basma could man the AB cosine when you baba man direction area okay. Don't forget it is this is the area normal to this. So the angle between B and the direction of the area is parallel. Parallel cosine is for the that'll be maximum here. What if, for example, we have some angle here? Let's say this one, yeah. If the magnetic field lines are tilted here, not perpendicular or directionally normally area or directionally magnetic field in this case, of course, it is going to be less than maximum. So we can say magnetic flux dakata AB cosine theta cosine b. You'll just write it down here. But what happens exactly if the magnetic field line are parallel to the cross-sectional area, baba? Cross-sectional area, if the magnetic field lines were parallel, on this magnetic field, direction area, which is here, perpendicular to the surface, the angle between the two is 90. We know that cosine 90 is 0. When you the bubbling magnetic flux, the 0. You can say AB cosine 90, that'll be the whole thing is 0. You might say, what exactly or why are we using this, baba? Because now, when a magnet is getting closer to a coil, magnetic field it increases and changes as long as the number of magnetic field lines that are passing through a coil, if it changes, that means there is a change in flux. There is a change in flux. Flux line magnetic field line pass through the coil change. Agar flux change between baba yani EMF درز دبي. EMF إيش درز بي if you have a closed circuit current درز دبي تنباشا. And that is exactly what we're going to learn here. But man, let's call it baba flux could to maximum if the magnetic field line if the magnetic field line are perpendicular to the cross-sectional area basha. Maximum if it is at some angle it's going to be between max and 0. When less than maximum, bigger than 0 obviously basha. Let's just say here change in flux will be bigger than 0 but less than max basha. Lera 0. Okay, what else do we need to know about it? Diagram is maximum plane perpendicular Basha, it is smaller if the plane is tilted, it is 0 if the plane is parallel. تقريبا هونش diagram كتابية لخوت عقالي بخرابني أوش وكو reminder بابا أو بسارة وزاري نشمان هي أبزمانش حالكين خراب نابي. The first one says the process of creating a current. Basha, the process of creating a current in a circuit loop by changing magnetic flux in a loop, kaka. What is it called? Is it called self-induction? No, we haven't studied this yet. Mutual induction, you haven't studied this yet. Electromagnetic induction, yes. Right, what about electrical superconductivity? No. All right. Consider conducting wires pulled through a magnetic field B as shown in the corresponding figure. The polarity, baba, of the induced EMF of which of the following is correct? Polarity mostly positive or negative. Which one of these wire is correct? Basha. Now yakshad bizana baba gutman. When we move a conductor inside a magnetic field, debita positive debita negative. Diagram how do I put a positive? How do I put a negative? Immediately this is impossible and we can cross these two out right away. It is one of the two. It is either A or B. How do we do that? Use the right hand rule. So directionally magnetic field is out of the page. Directionally motion is to the right. You can see that. As that if you do this, baba, magnetic field out of the page, this direction of the motion. If you do this, so positive will be pushed downward, negative will be upward. When with my negative upward, positive downward. So this is correct. What about the second one here? Now if you do this, positive negative this is incorrect. So the correct answer is A here. What about 3 says the magnitude of the induced electromotive force here in a straight conducting wire depends on what? Depends on equation whenever it says depends on madam dala wirish gutman EMF dakata B I L sine theta afu BLV, my bad. What am I writing here? BLV sine theta bashkaka kata depends on the length of a wire, yes. Depends on the strength of a magnetic field, yes. Depends on the velocity, let's say, with which the wire is moving through a magnetic field, yes. So kata debita all of them at this point right here. Zohar Basha. I believe this will be the end for this session, inshallah. Next time we're going to start with the change in the number of magnetic field line induces a current. Bash Baba. That'll be the end of this session. Stay tuned for more, inshallah. Stay tuned for more. I'll see you next time. Assalamu alaikum wa rahmatullah.